This is a rational function. What's the domain?
X can equal 3.
X
Yep.
equals cannot equal 3.
Nice. X not equal to 3. Anybody know the range? So remember what we're doing with inverse functions is we're swapping x and y. So what we do to find the range of a function is we find the domain of the inverse. So it should be y is not equal to -2. You can also see that particular piece in the horizontal asymptote, right? What is our horizontal asymptote here? So the mother function of the numerator is -2x, of the denominator is x, right? So there's my -2, there's my horizontal asymptote. I have a vertical asymptote at x equals 3. Yes, these are all related. Yep. What about x-intercept, y-intercept? How do you find the y-intercept?
Plug in 0 for x.
Plug in 0 for x. It's that simple. So I get -5/3, right? How do I get the x-intercept?
The equation equals to 0.
Set the numerator equal to 0, or the whole thing equal to 0. Of course, once you cross multiply, the denominator is gone. So what do I get? I get 2/5. Sorry, 5/2, 0. Is that right? Yeah. What's the short run at f of 3? What happens to my numerator?
It approaches -1.
Nice. So -1 over x minus 3. So you can see that mother function of -1 over x, right? So I'm ready to take a look at the graph. At 3, I've got a vertical asymptote. Now, of course, you can do all of this on your calculator, right? And I want you to. I want you to cheat. Just don't tell anybody. I told you that. But you want on the paper the evidence that you understand what the hell's going on. So y equals -2 is my horizontal asymptote. No problem, Alex.
Question about short run.
Yes, Alan.
Is short run just plugging into the numerator, or
Plugging in everywhere you can without getting a 0 in the denominator. So in this case, the only place I can plug in is in the numerator.
okay?
I've got a -5/3, right? And I have the 0.5/2, so it's 2.5, 0. But that's really giving me this confidence that I have my short run behavior right. So I know it's got to look like 1 over x, so it's got to be doing something like this, right? And I just missed the point, you know what I'm saying, right? It goes through that point and through this point. So there it is. There's my function. How do I know it's 1-to-1?
Multiply by the inverse.
You compose it. I would compose it
You
with
use
the
the
inverse.
horizontal line.
The horizontal line test, exactly. I want to use that horizontal line test. No matter where I draw a horizontal line, it hits one height. And that's what I need. I need no heights to be repeated. If heights are repeated, then I no longer, the inverse won't be a function. It'll be confused. Sometimes I'll put money in and get a soda out. Sometimes I'll put money in and get a live chicken out. Right? So I need the inverse to be a function. Sometimes we can find the inverse, but it's not a function. Weird. A little weird thought, but. And so then there's trouble at times, right? So we know that this is 1-to-1. It passes the horizontal line test. Let's prove it's 1-to-1. How do I prove it's 1-to-1?
Find F F inverse.
Yes, I could find the inverse, but I want to actually I want to prove it's 1-to-1 before I go looking, because what if it's not? Then I'm looking for something that doesn't exist, right? So I want to prove it's 1-to-1 first. How do I do that?
FA has to be equal to FB.
Nice. Let f of a equal f of b. Those are y values. Y values equal should mean the x values are equal. So I get 5 minus 2a over a minus 3 is going to be equal to 5 minus 2b over b minus 3. Not that I don't like fractions, but I'd like to get rid of them, so I cross multiply, right? Everybody with me?
Yeah.
So I get 5 minus 2a times b minus 3 should equal 5 minus 2b times a minus 3. And I don't know why there's so many private conversations going on with these terms here. So let's break up the parenthesis, right? We get 5b minus 15 minus 2ab plus 6a should equal 5a minus 15 minus 2ab plus 6b. Those arrows are there for me to know that I've covered everything, right? They're there for me to know that I've distributed correctly. So then I can see that I get some things to cancel here, right? It looks like I have 2ab on both sides, that goes away, and a 15 on both sides, that goes away. So I've got 5b plus 6a equals 5a plus 6b. And I want to try and get everything on one side, minimizing the number of negatives. So it looks like I can get 6a minus 5a on the left and 6b minus 5b on the right. So I've got a equals b done. Nice. So it's 1-to-1. Once I know it's 1-to-1, what do I know? Once I know a function is 1-to-1, what do I know about the function?
That there is an F inverse.
That there's an inverse, and now I want to be able to find the inverse, right? Since f is 1-to-1, f inverse exists. Might not be easy to find at times, and you'll see when you do some of these in your calc class, you'll see that using the inverse functions sometimes get a little tricky. So what do? I start with f of x, and I replace f with a y. Some teachers will say, okay, switch x and y and then solve for y. I just say solve for x and then switch. It doesn't matter. So let's solve for x here. I get y times x minus 3 equals 5 minus 2x. Again, I'm trying to get rid of the fractions, get rid of the parentheses. I get xy minus 3y equals 5 minus 2x. Is everybody with me here?
Yes.
Am I going a little fast for anyone?
Yes. Can you do that again?
Yes, yes. So right here, I start with my function, right? And then I instead of using the function notation, I go back to my old notation of y. Y is f of x. And then I cross multiply, right? You can see this x minus 3 coming up to be multiplied here.
Mhm.
Then I distribute the y, and that's where I'm at right now. And remember, I'm trying to solve for x, so I want to gather my x terms on one side, and I'm trying to minimize the number of negatives. If I moved all my x terms to the right, everything would have a negative sign on it. If I move them to the left, nothing has a negative sign. That's kind of nice. Right? So I moved my 2x from the right to the left. That became a positive 2x. I moved my 3y from the left to the right. That became a positive 3y. And now I'm going to do something that begins with an F and ends with a Tom Cruise. Begins with an F, ends with Sidney Poitier. Begins with an F, ends with an actor.
Factor.
Factor. Yeah. So x times y plus 2 equals 5 plus 3y. Again, I'm solving for x. X equals 5 plus 3y, all divided by y plus 2. Now switch my x and y. Once I get there, I switch my x and y. And I call that my inverse. Now notice the domain of the inverse. Notice the domain of the inverse. X can't be what?
3.
Negative.
Negative 2. Sorry.
Negative 2. And that is the range of my original function. Because when you're finding an inverse, you're switching x's and y's. You're switching your domain and range. So if you want the range of your function, you're finding the domain of the inverse. Now, we've got a couple of ways to do a quick double check, right? We've got a couple of ways to do a really quick double check on does this work? And then we have an official way to find out if we actually have the inverse or not, right? So the quick double check is just to pick a value in the domain of f, see what the output is, take the output, put it in the inverse, and see what that output is, and see if they switch, right? So let me write my functions again here. F of x was 5 minus 2x over x minus 3. And f inverse, oops, sorry, which I'd rather call g, is 5 plus 3x over x plus 2. So who's got a value in the domain for me?
Zero.
Sure. So f of 0 is 5 minus 2 times 0 over 0 minus 3. That's negative 5/3. And now let's find g of negative 5/3. Is everybody with me here? You can pick anything in the domain of f, right? The only problem is you can't pick everything. That's the problem. It takes too long, right? So I've got 5 plus 3 times a minus 5/3 over minus 5/3 plus 2. That's 0 over who cares, right?
What are your priorities, girl?
So 0. right? So our input-output switched, which is what we thought would happen, right? Now, we still aren't guaranteed we have an inverse. We think it is. So what we do is we compose these two functions and then show that what should I get as a result when I compose them.
X equals 0.
X
Yeah,
equals 1.
No. So when I did it with the numbers, I started with 0 and I got back to 0, right? All right. So when I'm doing it with general functions, what am I starting? What's my input?
GX.
At just x. And so that's what I should get at the end, right? So if I look at the composition f composed of g of x, yes, what's the input of f? I agree, it's g. But what's the input of g? That's just x. So that's what I'm expecting. What's the absolute inner point is an x. That's what I should get out when I compose inverse functions with each other. So f is 5 minus 2 times x all over x minus 3. And I'm putting in the inverse there. I remember myself used to say put in the g. So I would just, this is how I get myself to understand what was really going on, right? Because I got confused a lot. So I want to see, I can see in black the original function and what's the input is g, right? I don't know why I had to do that, but I did. So my function g is 5 plus 3x over x plus 2. And I'm going to try and find the interior LCD here. Well, it turns out just to be x plus 2, so I'm going to multiply by 1 in the form of x plus 2 over itself. And I'm going to distribute this in now, right? So without skipping steps, I get 5 times an x plus 2 in parens minus 2 times x plus 2 times that original function g, 5 plus 3x over x plus 2. Right, and I can clearly see that those x plus 2's there are going to cancel. But I'm just trying not to skip any steps here. So I'm multiplying this x plus 2 in, and I already had in green this 5 plus 3x over x plus 2. Right? So I'm trying to really stay organized. I don't care about wasting paper. I don't care if my test solutions, are 20 pages long. If you're still having file size issues, please download CamScanner. It's the best way to go. So I know these are canceling here, and I'm trying to take my time here. So I get 5 times x plus 2 minus 2 times the 5 plus 3x. That's my numerator now. Downstairs I have a 5 plus 3x. Oops, minus 3 times x plus 2. As I'm rewriting, I'm not trying to distribute it all. I'm just, simply writing everything, trying to do baby steps. 5x plus 10 minus 10 minus 6x. 5 plus 3x minus 6x minus 6.
It's just minus 3x.
Thank you. I thought something looked weird. Yes, you're right. Right there where I messed up, right? So, lots of things go away. It looks like my 10s go away here, and my 3x's go away here. And it looks like I get negative x over negative 1, which is just x. Nice. Remember, I must do the other composition as well, g composed of f. I should get the same result, and when I do, I can finally conclude that I have definitely found my inverse function. How are we doing?
Seems straightforward.
Yeah, makes sense.
This is the first question on your test 3. Something just like this. All right, we're ready for new stuff. My goal is to teach 5.3 and 5.4 today. I don't know if I'll get it all done, but you're going to definitely let me know if I'm going too fast or if I'm doing something that you don't understand. I don't think 5.3 is difficult. We're talking about exponential functions. And it turns out 5.4 is logarithmic functions, and they turn out to be inverse of each other, right? Which is why we just did all this inverse stuff first. So I want to look at the general form of an exponential function. F of x equals c times a to the x is exponential. Where 0c right, is the y-intercept, or initial value. They call c the initial value. A is a real number not equal to 0 or 1. A is in the positive reals, not 0 or 1. So A is the base. If A is between 0 and 1, the function is decreasing. If A is bigger than 1, the function is increasing. And of course, it's an exponential function. My variable is the exponent, right? So if I just took y equals 1 to the x as my function, 1 to any power is going to be 1. This is a constant. We don't care about it, right? So this is just boring, right? If I let the base be 0, I don't have a problem, right? 0 to any positive power is not a problem. But 0 to a negative power, right? Like minus 1/2, right? Well, that's 1 over the square root of 0. That's trouble. So we don't want our base to be 0. We don't want our base to be 1. We don't want our base to be 0. And it's all about the base, Why can't I let my base be a negative number? Because, again, when I put a negative x into my, when I put a negative number into that, I'm now I could have a square root of a negative. And, we're trying to keep everything real. So basically, the function, looks like this with 0, c. What else can I see here? That I have a horizontal asymptote. Maybe I even want to say y equals c a to the x plus b, where b is the horizontal asymptote, right? What's my domain? Everything. What's my range?
Everything above the horizontal asymptote.
Exactly. So from b to infinity. So because we're going to be looking at translations of this function, we want to be able to take all of this information and translate it when I give you a translation of the function. So, and that's something that's going to happen a lot. Now, remember, what are you going to do? You're going to put this stuff in your calculator, right? You're going to put it in your calculator, and the calculator will then help you get down on paper all of the information and all of the proof of your understanding of what's going on in the exponential function. So, for example, I might have y equals 3 times 2 to the x minus 1 minus 4. So there's my exponential function. The base is 2, fine. The initial value is 3. What happened to my my origin, though? Where did it move?
Down 4.
Yep. So in this particular case, I'm really looking at this this 1 by 1 box again, right? So there's my 1 by 1 box, and here is my function y equals 2 to the x. What happens when I bring in this multiplier of 3 times 2 to the x? What's it do to my curve?
Shifts it up 3.
Yep, stretches it. So there's my function y equals 3 times 2 to the x. And now where does my box move?
Down 3.
Down 4.
Oh, yeah, my bad, 4.
Yep, down 4 over 1. Oops, missed again. Where is my over 1 coming from?
The 2 to the x minus 1.
Yeah, so that x minus 1 means move 1 to the right, right? X's behave inversely. And what is my domain? How wide does that graph get?
All real numbers.
What's my range?
From -4 to infinity.
There you go. Nice. All of this clearly visible on the graph, right? But this is one of the things I should be able to talk about when I look at an exponential function. So I guess we better graph one by hand, right, using a table of values. So let's do that. Let's start with a nice simple function and graph it, right? So let's take y equals 2 to the x as our exponential. Let's generate a table of values. So -2, -1, 0, 1, 2. Typically, I'll do some kind of table like that. I know when I plug in 0, I'll get the initial value of 1, right? And when I plug in 1, I get 2. When I plug in 2, I get 4. And when I plug in -1, I get 1/2 and 1/4 when I plug in -2. So I'm going to graph those as best I can. So at 0, I get 1. At 1, I get 2. At 2, I get 4. At -1, I get 1/2. At -2, I get 1/4. So there's my exponential function. Now we're going to be looking at the inverse function of this, right? And what's special about the inverse function? Well, it's going to reflect on the line y equals x, right? So this y equals x piece will always be the way I mirror my x and y, my points, right, for the function and its inverse function. So it turns out that this inverse function, so y equals 2 to the x and y equals log base 2 of x are inverse functions. And I can already see the points on my log base 2 function, right? So obviously log base 2, obviously the base is 2, right? So, but I already have a table ready for me, right? My table is all set already. My x's and y's are just going to switch, right? So -2, -1, 0, 1, and 2. And then my y values become my input, 1, 2, 4, and then 1/2, 1/4. So I certainly can plug those points in. I have a 0, 1 on my exponential curve. I have a 1, 0 on my logarithmic curve. I have a 1, 2 on my exponential. I have a 2, 1 on my log, right?
Professor, can you put the keyboard down?
Yes, sorry. Thank you. And there it is. There's y equals log base 2 of x. Notice that the horizontal asymptote of my 2 to the x became the vertical asymptote of log, right? Of the log function. So I'm going to give you a function. You're going to graph it. You're going to tell me domain. You're going to tell me range. You're going to, just give the computer whatever it wants. I can't really see me asking you a question like this. It's too easy in a test. But sorry, I just lost my book. But when we get to the second test question, I'll let you know, okay? So exponential functions. Notice what's happening in my exponential function. What's happening with the outputs? What's going on with the outputs?
They're getting bigger.
Okay, good. How am I getting from one to the next?
You multiply by 2.
Okay, multiplying. Remember when I had a linear function, I was adding, right?
Mm-hmm.
So in exponentials, I'm multiplying. In linears, I am adding. Right. So so that's one of the questions. They're gonna give you a table and they're gonna ask you, is it an exponential function? Is it a linear function? Or is it neither of those? Right? Let's do one like that real quick. This is not the most exciting bit of material, but when we get to 5, 6, that's where the fun happens. And again, it's me talking. Well, it might not be fun for you, but so I'm just looking at a couple of homeworks. This is homework 22, section 5.3. After today, you should be able to do up to homework 22. So it's asking, is this thing linear? Is this thing linear, or is it
Exponential.
exponential, or is it neither? So looking from 4 to 8, I could be adding 4, but then am I adding 4 to get from 8 to 16? No. So from 4 to 8 could be multiplying by 2. 8 times 2 is 16. Is 16 times 2 24?
No.
No. So it looks like we don't have a linear or an exponential here. For the exponential, I need everything to be multiplied by the same number. For the linear, I need everything to be adding the same number. This one, what do you think? Am I adding the same thing? 1 plus 10 is 11. Is 11 plus 10 121? No. So then I'm asking, next thing I'm asking is, am I multiplying by 11 every time here?
Yes.
Yes. So I'm pretty sure my base is 1 over 11, right? The base is 1 over 11 for this particular function. Let's see, I had an xy, right? And I had 1 over 11. I had, I forget already, was it 1? Yep, 1, and then 11. And then 121, right? And I have to figure out y equals c a to the x. So I think I got the a as 1 over 11, right? So I just now have to figure out that initial value. And obviously you can see the initial value here, but I might have to plug in a point to really think about it. C should be 1, right? So we had a is 1 over 11, c is 1, and then I'm done. Y equals 1 over 11 to the x. And of course I could rewrite this. What's another way of rewriting this?
Y equals log 1 over 11 x. No.
So if you're thinking the inverse, right? But I'm just saying rewrite this, make this a little bit easier. I can write this as 11 to what power?
-1.
Almost negative x,
Negative.
right? Yeah, I guess I skipped a step there. So 1 over 11 is the same as 11 over 1 to the -1. And then I'm multiplying the bases, the exponents, right? The book would accept either answer. The book, MathXL would accept either one. You know, I'm just trying to write things with the least number of pen strokes for the least amount of code.
Well, the least amount of code would actually be leaving it in its most awful state, because that's the least amount you have to do.
Yeah, but we're always interested in the last result having the least strokes, not counting all of the strokes until I got to that last result. I understand what you're saying. So there's a bunch of questions like that. And then there's a bunch of questions like this. These are very insulting, so I apologize about them. But exponential functions are 1 to 1. Is that true? Look at this. Look at my functions I've given you so far today. Exponential functions are 1 to 1. Is that true?
Yes.
Logarithmic functions are 1 to 1. It turns out that they're the inverse of each other, so they had better be 1 to 1, or the inverses wouldn't even exist, right? So when I know a function is 1 to 1, right? So this is solving simple exponential equations. if I have 7 to the x equals 7 to the third, I have exponential functions here. They are 1 to 1. Are these y values or are these x values?
Y values.
They're y values. This is the whole function, the outside, right? So what does this have to imply to me? That x equals 3. So when I have exponential functions set equal to each other, right, and they're the same base, my exponents must be equal to each other. So that one's kind of insulting, but the whole idea that I want you to get is that because I have one-to-one functions, I know the inputs have to be the same, right? When the outputs are the same, the inputs have to be the same. Here's one that's a little bit more difficult. 5 to the 4x plus 1 equals 25. 5 to the 4x plus 1 equals 25. Are these the same base? Are these functions the same base?
No.
So what is the base on the left?
5.
5. Good. What's the base on the right?
25.
Almost.
5.
5. Yeah, it's 5. And all of these, they're going to make them look tricky, but they're all going to have the same base for me to solve them until I get to section 5-6. So this one is 5 squared over here. Right, 5 squared is 25. So now I can see that I have the same base. I know exponential functions are 1 to 1, so that means I know my exponents have to be equal, right? Once I get this, I know my exponents have to be equal. 4x plus 1 has got to be equal to 2. So what is that? X is 1/4? When I'm solving these, I want to check, okay? Because once I start solving logarithmic equations, I'm going to get something called an extraneous answer. I'm going to get an answer from the algebra, but when I plug that answer back in, it's not going to work. These problems that the book is giving you, all of these will work. Okay, I think so. Let me double check that. Here's one. So I've got e to the, I've lost it already, sorry. E to the x squared equals e to the 14x times 1 over e to the 48. And again, e is just a number, right? We talked about that. We'll talk about it in a little bit more detail today, I think. But remember, e is just a number. It's about 2.72. It's as famous as pi, pi being related to circles in geometry, e being related to finance. So I have the same base. What's the base here? Yeah. So I'm just trying to get it to a single base on both sides. So I can bring up that e by changing my exponent to negative. And now when I'm multiplying like bases, what do I do with the exponents?
Do you set them equal to each other?
I add them, right? When I'm multiplying, so look at drunk Aunt Sally. Please excuse my drunk Aunt Sally. When I'm multiplying like bases, I add the exponents.
Okay.
You always go down a level for those exponential pieces. When I'm adding like bases, what do I do with the exponents? So like x squared plus x cubed, what do I do to the exponents? What's my arrow say?
You add.
Unchanged.
When I'm multiplying, I add. When I'm adding, what do I do?
Nothing.
Nothing.
Stays
Nothing. Exactly nothing. I can't do anything with them. So now, because my pieces here are 1 to 1, I know x squared has to equal 14x minus 48. Oh, that's an old quadratic friend of mine, right? Equal to 0. I'm looking for numbers that multiply to 48 and add to 14. Three and 16. Yep. 4 and 12. 5 doesn't go in. 6 and 8. There it is, right? So I know I've got x minus 6, x minus 8 equals 0. Right? 6 times 8 is 48. Negative times negative is positive. Negative 6 and negative 8 is negative 14. So I get answers of x equals 6 and x equals 8. And yes, both of those work. But you want to be careful once we start doing these equations. Sometimes you'll get answers that make sense when you do the algebra, but when you plug them back in, they don't. Okay? Extraneous answers, extraneous solutions. Nice. That's easy homework. Easy homework there. Homework 20. I think it was homework 20. I don't know why I put the numbers on, but I did. I could have just said homework 5.3, right? Everybody's here today. Is that true? 4, 8, 12, 16, 20. No, almost everybody. Nice. I think that's it for that section. Let me double check. I might want to talk about E, where E is coming from again. Let me just check the textbook real quick. Just 1 second, please. Oh, yeah. Yeah, let me do one more thing in this section, and then we'll move on to the next section 5.4. The thing I want to do is talk about E, where this number comes from. And so I want to go back to simple investing, right? So if I invest, I'll get an amount out. If I put a principal in, I'm going to put it like $100 in, right? And so I get that first piece. No, let me, I'm lost. Give me a second. Is it 1 plus r to the nt? One plus r over n. All right, so there's my general interest formula, where t is time in years, right? R is the interest rate. P is the principal, the initial amount of money I put in, right? And n is the number of times compounded. So if I compound quarterly, 4 times a year. If I compound monthly, 12 times a year, right? Compound daily, 365 days a year, kind of thing, right? So number of times compounded. So meaning how often do I calculate the interest, right? So like you buy
Professor?
something. Yes.
What's that at the beginning? Like
A.
I can't tell.
An amount.
A,
An
okay.
amount. Yeah, sorry.
All right, got it.
So the amount in the bank, right?
Right. Yeah.
Or the amount on
this
your
formula is familiar.
Yes, or the amount on your credit card, right? So if you buy something on your credit card for $100 and don't pay it off, you now owe the original amount plus the interest, and they've compounded it once, right? And so when they compound it the next month, right, what's happening is they're taking the interest that they've charged you gets calculated. Now you owe them that too, right? That's this compounding piece, right? So let's look at this as not as a debt. Let's look at it as a good situation. Let's invest, right? Let's invest $1 for 1 year, and let's take an interest rate of 100%. Sounds good. We're going to put in $1 for 1 year with an interest rate of 100%, and I'm going to calculate the interest an infinite number of times. So I'm going to let n be compounded not every month, not every day, not every hour, not every second, not every millisecond. It's going to be compounded an infinite number of times. So the amount I'm going to get at the end is going to be 1 plus 1 over n to the n as n goes to infinity. Let's go to our calculators. And I want to put in the 1 plus 1 over x. I can't use n, right? 1 divided by x, close parenthesis, raised to the x. And everybody with me there? I want to take my window, my table set, and I want to be in control of it. So I'm going to say, make my independent let the calculator ask me for the independent variable. So for the values of x, for the number of times I compound. And now look at my table. So it's ready for me to compound it once. So let's compound it once. I hit 1 and I hit enter. So, right, if I compound it once, how much money did I put it in again? $1, right?
Yeah.
And for 1 year, and I only compounded once, but my interest rate was 100%. So how much do I get back? I get $2 back. I get my original plus the 100% interest. Let me do 5 years. 2.49. Let me do 1,000 years. Sorry, not years, times compounded. So compounded 5 times, I only got up to $2.49. Compounded 1,000 times, $2.72. Let's compound it 5 million times. There it is, 5 million times. It's E, 2.72. No matter how many times I compound it, I've hit this max level of return on my investment. And it's this number E. It's crazy. All right, let's talk about 5-4 logarithmic functions. Sorry, this stuff is so boring today, but
You're good.
I'm bored. Logarithmic functions. So we already know, because I told you, that exponential functions have inverses called logarithmic functions, and vice versa. Log functions have inverses called exponential functions. And so the first thing we want to do is think about the translation between them. So we're going to say that y equals b to the x is our exponential. And log base b of y is x is the logarithmic function. And they're equivalent, right? This double arrow means they're equivalent, right? They're logically equivalent. They're inverses of each other, okay? Notice what's the input in the exponential function.
X.
The x. And because they're inverses, the input of the log function is the y. But what's the output of the log function? Look at the output of the log function.
X.
Ah, so a logarithmic function actually is what? What is the x for the exponential function?
It's the exponent.
Exactly. That's what a log is. A log is simply the exponent. So it will help you when we get into some things that are a little bit more complicated to know that all you're dealing with are exponents. When I'm dealing with log functions, I'm dealing with an exponent, right? So this translation is very important to us. And that's one of the first things you do is just simply translate. So let's take a look at a couple of problems here in the homework. My mouse is dying. It's driving me crazy. So the very first thing that we want to be able to do is translate. And in fact, just like when we learned to speak a language, right? When we learned to speak a language, when we would be saying something out loud in the new language, we'd still have the other translation in our head. Does anybody agree with me on that? Anybody? So like when I'm first learning how to curse and when
How I feel when
Yeah.
Could you repeat that again?
Yeah. So when I first learned how to curse in French, when I'm saying the curse word out loud, inside of my head, I'm saying the curse word in English to myself.
Got
Right?
it.
And so this is what I want us to do, is when we see something as a log function, we don't really understand it yet. We're just learning these now. We're going to translate it into an exponential, which we do understand. Exponentials
Okay.
are simple, right?
Right.
So, like when I was learning Spanish, well, I failed Spanish in high school every year, but I remember, what is it? Who speaks Spanish? Anybody speak Spanish?
I speak
What
Spanish.
does Yoda say mean?
I don't know.
I thought you said you spoke Spanish.
Oh my God.
So looking at a couple of these problems here in section 5.4, I simply can see this as an exponential. 7 to the third power. There's my exponent is 3. The base is 7. The result is 343. I would like to be able to write this as a log, right? So I said, what? 343 equals 7 cubed, right? And I want to write this over using that translation, right? And so what is it? Log base what?
Log base 7.
Exactly. So I get the base from the exponential. So that log is like a little subscript, right? Log base 7 of, well, I know the answer to a log problem is the exponent. So I know the answer is 3. So what's the argument here? It's going to be 343. Right? What's the input? Is the output of the exponential. Let's do another one. Pretty simple, right?
Yeah.
So this one makes a lot more sense. This one, I read this one. Log base 6 of 36 is 2, right? Log base 6, I know the base is 6. I know the answer to a log problem is an exponent, right? And then all I'm left with is my last choice. So log base 6 of 36 is 2. Log base 6 of 36 is 2. I want to translate this because it doesn't make a lot of sense to me yet. But if I write it as an exponent, it will. What's my base?
6.
What's the exponent?
2. 2.
6 squared is what?
6.
Look at, see,
36.
you see how easy, when I'm looking at that as the form of a log equation, I'm going, what the hell does it say? But when I look at it as an exponential, it's very, very easy, right? And so this is the key, is this translation is key, because right now, as you are a math student, you're just going to be learning this translation. And then later on, right, when you're doing all of these physics applications, right, and I'm talking about the engineers here, you're going to have to be able to think in terms of logs, okay? So, but right now, I'm just saying to you, translate it, right? I'll give it to you one way, you give it to me the other way. If I give it to you as a log and you have no idea what it means, translate it, and then you will easily. Now, there's a bunch of special bases for logs. And so if I say log base 10, right, of x, that's the same as just writing log of x. So base 10 is very special to us, right? Obviously, 10 fingers. So instead of writing log base 10, we just write log. And log base e, because e is very special, a very special number when it comes to exponential growth, money, populations, things like that. We call that one ln, the natural log ln of x. And you'll see on your calculator you have both of those. You have a log function and you have an ln function. So the log is log base 10, ln is log base e, the natural log. Stuff it's a little bit, it's easy, right? It's very easy right now, but it's weird because you haven't done it before. So you just have to have a clear guide of what to do. So this one they want me to solve for x, but I don't think in logs yet, not yet, right? So I want to translate this. So what's my base here? What's my base?
4.
Good. What's the exponent?
X.
What's the answer?
16.
Okay. So now we're back to where we were before. 4 to the x is 16. We know the answer is 2, but I'm going, okay, this is 2 squared to the x, and this is 2 to the 4th, right? Yes. And so I get 2 to the 2x equals 2 to the 4th. So I know 2x is 4 or x is 2. Now that one, couldn't I just answer right away? Yes. But the ones I'm going to give you, you're not going to be able to. You'd have to do this process, right? So right now we only have one process, and that is if we have the same base, right? Get it written to the same base, and then set the exponents equal to each other and solve it. And again, this one you could have done in your head. But the ones that we're going to get to in section 5-6, you cannot do in your head. They're too difficult, okay? We're almost done today, which is awesome. So what do you want to call this? Log base 5 of 1. Log base 5 of 1. What do you want to call the answer? What? We don't know the answer, so let's give it a letter. What do you want to call the letter?
X.
Thanks. So we're going to translate. Base 5, so 5 to the x is 1. Now what is x?
0.
Yep.
0.
Yep. So when you translate it, it gets very easy. Here we go. The natural log of the 12th root of e. The natural log, ln, of the 12th root of e. What do you want to call this answer? George, whatever, right? Anything you want, let's call it x. What's the base?
I want to say 1.
Not 1. So ln is one of these special ones.
E.
E. So e to the x has to equal 12th root of e. Well, 12th root can be written as a 1/12 exponent. So what is x? Very easy. It's very easy. It's kind of insulting. I'm sorry. I don't mean to insult you.
X equals 1/12.
Yeah. So I don't mean to insult you. I promise you it will get more difficult on Friday. So right now it's just a little bit offensive. It's too easy. But the key is the translation. That's what we have to keep in mind, that translation, right? This one's interesting. Find the domain of this function. This is the ln of x plus 1, right? So y equals ln of x plus 1. Well, I don't know how to find it. I don't know how. So what should I do? Well, I mean, I could graph it and find it. But what should I do here? What do you think? What have we been doing?
Are you trying to find like the exponent, like the exponential function?
Exactly. Switch it to the exponential function. So if I want the domain of this, right? So the domain of y is my question. right? What I can do is look at the range of the exponential function, and that's the domain of this one. So how do I translate this?
Okay.
What's the base?
The base is e.
Good. The exponent is my y, and the argument is
X plus 1.
Nice. Remember, I'm switching x's and y's here, so I can switch them anytime. So e to the x is y plus 1. So that means my exponential function is e to the x all minus 1. And there it is. There's my inverse function.
Okay.
Now look at the graph of the inverse function. Well, I knew my horizontal asymptote was 0, but now it's switched to 1. I'm sorry, minus 1, right? It's moved down, right? And what is this range? This range goes from minus 1 to infinity. Oops. This range goes from minus 1 to infinity, which means my domain is minus 1 to infinity. I switch it to the exponential, I solve things using the exponential, and then I'm able to translate it back into the logarithmic. It takes practice, takes some patience, right? You're never going to be a doctor if you don't have patience. So you have to, you have to think, okay? You have to think a little bit. That's a tricky one. I'll let you do that one. All right, we're done for today. I'll see y'all Friday. We're going to have an observation, someone observing us Friday. Well, observing me, but just be yourselves, okay? See you Friday.
Bye, Professor.
Have a good one, Professor.
Professor.
Yes. What's up? Oh, thank you. Bye.
Professor, do you mind if I stay a couple of minutes?
Not at all.
I got here
Yeah, not at all.
a little bit late. I sent you an
Yes.
email.
And I recorded. Yeah, I knew you'd be a little late today. It's okay.
Okay.
The first thing I did was and I'm showing it on my screen here, is I redid the main problem from Monday.
Uh-huh.
All right, so the first thing I did was we got a rational function, we graphed it, we proved it was 1-to-1, then we found the inverse and all of that. And then I just started talking about, that was all, then I just started talking about exponential functions. And this is probably the main thing that you missed, is just that, I'm always going to have this domain and this range, and then I'm going to just shift it like I did today. We had the e to the x minus 1, so I knew the graph moved down 1. And so, I think that's the main thing you missed. So here's me starting with a simple function in green, y equals 2 to the x.
Mm-hmm.
And you see my square there, my 1-by-1 square?
Yeah.
That's that same one I used with the other mother functions, because I'm gonna be focused on that and where does that move, right?
Right.
So what happened? Oh, I guess I didn't do that part. What happened to my square when I multiplied it by 3, right? It's at a height of 3 now.
Mm-hmm.
I should have had that here like that. And then I moved it over 1 from the x minus 1, right? Remember, x's behave inversely. And then down 4.
Down.
Right, down 4 because of that. Yeah.
So to move it, so like in the black equation right there on the left, to move it to the right, you have to subtract from x.
Yes.
Yeah. Okay.
Remember,
it's just a little weird seeing it on the exponent.
Yes, exactly. But the same concept as before. Right. I like to think of exponential functions kind of like a soda machine, in that you always put the money at the top right of the soda machine. Mm-hmm. So that's kind of where well, we used to when we had coins, but you can see where the input is. So
okay.
so you can kind of see that coin slot for the for the money as where your input is.
Uh-huh.
Yeah, so that should make it clearer that's moving left or right, and then that thing on the outside, that's a y value, right? Because that 4 is on the outside of the function. So on the outside, it has to be a y value, so that's me moving up or down.
Okay, I got it.
Yeah, this section is good for you to read. It's not difficult at all. 5.3 and 5.4, and then I think you came in once I started doing.
Yeah, I came in right there.
Yeah.
Okay. All right.
All right, and it's recorded. Oh, actually, I'm still recording.